The basic rules of determining the derivative of a function and their geometrical interpretation are somewhat familiar to many. Also, what happens to the derivative of functions if they undergo modifications like addition or multiplication of two functions is taught already at high school level. And there are a lot of great videos out there on this topic trying to provide visual intuition. But I hope I can add at least a tiny new twist and add a perspective some viewers might not yet have had. And in this video, I'd like to talk about the chain rule, the rule to determine the derivative of nested, or in other terminology, composed functions. Before we start, a few disclaimers. This video does not present fundamentally new ways of deriving the chain rule. Also, it would be ridiculous to assume that nobody else has ever thought of doing visualizations similar to this video. As said though, I hope to add a tiny twist to what I've found so far. Second, as you will probably have guessed by now, this video is not a full introduction to the chain rule. To get something out of it, you should have understood at least the concept of a derivative, and ideally, you should already have taken in some info on the chain rule in particular. Third, a visualization does not replace a rigorous proof. This video in particular will cut back on formalism for the sake of intuition. And finally, if at any point you feel this video doesn't tell you anything new or makes your confusion worse, feel free to step out at any time. But of course, I'd be glad if you make it to the end. So let's start with two nested functions. A function f of x, a function g of x, and their composition g of f of x. Let's ignore which functions exactly we're seeing here. As it is all about visualization, the exact formulas shouldn't matter. I'm certainly guilty, though, of having deliberately selected something that looks a little cluttered. And indeed, it might be hard to see at first glance how f, g, and g of f are related, even if we know that the function value of f at any location x is fed into g to obtain g of f of x. Does it help when we mark the function value of f as well? To me that looks still quite confusing. We know that the value of f gets fed into g as some intermediate x, but can we see this? Well, this transfer literally means using some y value as an x value, and that should ring a bell. There's a function which does just that, probably our most beloved linear function of all times. Now we can take the y equals f of x value, shoot a horizontal ray towards x equals y, and the vertical reflection intersects with g just where we need to take the g value. So here we have it. The relevant points of f at x, g of f at x, and g at the intermediate x location always form a rectangle whose fourth corner lies on the y equals x diagonal. Okay, fine, but does that help with understanding the derivative of g of f? Well, that's of course for you to decide, so let's try. Here, we've got the widely known setup with the sum dx, the resulting deltas in the function values, and the secant slopes. And I'm using a ridiculously large dx for better visibility. Remember, the whole concept of a derivative is obtaining the slope of the tangent by letting dx approach 0. I've used arrows instead of simple line segments, which should come in handy later when we look at some example x values and need to keep track of changing signs. At this point, let's just very briefly use this setup to get to the formula of g of f prime with as little formalism as possible. Remember, g of f prime of x is the tangent slope at the horizontal position x. And by slope, I mean the ratio between a change in y, that is function value, and a change in x, the horizontal position. We know from the general concept of the derivative that the slope of the secant between x and x plus dx approaches this tangent slope as dx tends to 0. So let's look at the situation before this limit process, when dx has some positive, albeit small value. We start with the secant slope of g of f at the location x. This can be calculated as dg of f over dx at this x position. The dg of f part is equal to dg at the intermediate x position. The dg is equal to the slope of the secant of g at the intermediate x times this little dx intermediate, which we'll get to in a moment. Which intermediate x exactly? Well, xi equals f of x, of course. And what about the intermediate dx? Well, that's our df value at the original x position, which is calculated as dx times the slope of the secant of f at x. Conveniently, the dx's cancel. The equation we've obtained so far is for the case where dx and all the other d's still haven't approached zero. Now let's look at what happens to the different parts of the equation in the limit process. The slope of the secant of g of f at x approaches the slope of the tangent at this position. Likewise, the secant slopes of g at f of x and of f itself at x approach their tangent values. But the slope values at all the respective horizontal positions are just the derivative values. And there we have it, the formula for the derivative of a nested function. Pretty hand-wavy and informally, but hopefully providing a little more visual intuition. While we're in the setup, let's look at a few example x positions to see qualitatively how the slopes of f and g influence the resulting slope at g of f. Already at the current x position, we can see an interesting effect. The slope of f at this point is pretty shallow, so we obtain a pretty small df and thereby dxi. The steep slope of g at the position xi equals f of x blows that up into quite a big dg. But in the end, we're taking this dg over our original dx, which is larger, resulting in a medium slope of g of f. Now let's move to a different x position. Here, the slope of f is negative, leading to a negative df, and hence to negative dxi at g of xi, indicated by an arrow that points to the left instead of the right. That, together with the positive slope of g at xi equals f of x, leads to a negative dg and dg of f, and hence to a negative slope of g of f at x. And maybe some final example. Here again, the slope of f at x is negative, but this time the slope of g at xi equals f of x is negative as well. So the leftward pointing dxi leads to a positive dg and dg of f, resulting in a positive slope of g of f at x. So, hopefully this visualization provided a bit of added intuition for some people. But maybe this view is too cluttered for you, and you would also like to take a step back and get a more bird's eye perspective. And that's why I'd like to try something else yet. Namely, enlist the help of an additional dimension. Instead of obtaining x intermediate by reflection on the y equals x line, we might as well give it its own dimension. Now f lives in the xi plane, whereas g lives in the xi y plane. Now we can execute our geometrical construction to obtain g of f of x more directly. Okay, but where's the promised bird's eye perspective? Well, to start with, I said g lives in the xi y plane, but more precisely speaking, it lives in every plane parallel to this one, namely for each x position, and thereby traces this surface, or 2D manifold, in 3D space. Likewise, the ray from the f of x position to g at xi equals f of x traces this surface. Their intersection, traced by the point where the ray meets g, is this curve or 1D manifold in 3D space. The projection of this curve back onto the xy plane creates our composed function g of f of x. I think this view has some potential for showing what function composition does, but for this, let's use a simpler inner function. Let's even start with a seemingly unnested function. I think you may have heard that any function g of x can be moved leftwards or rightwards by adding some constant to x. Has it ever appeared slightly counterintuitive to you that by adding something negative, you move the function rightwards and vice versa? Likewise, multiplying x by some constant can stretch or squeeze the function. Here again, the larger values lead to squeezing. Funny, right? We can consider this addition and multiplication as an inner function. We can use our 3D setup to make the effect of f's horizontal offset and slope more palpable. Now it becomes clear how the surface traced by f intersects the surface traced by g differently depending on the f offset. Likewise, a higher slope of f leads to the f surface intersecting a larger range of the g surface on the same x range. For the end, let's go back to our original g and f. We still need to look at the dx and slope line setup. You already know how they work from the 2D setup, so I'll just leave you with this perspective. I hope one or both of the visualizations could provide some additional intuition. Thanks for watching, and bye-bye.